All right, thank you for the introduction and welcome to my talk on SpringFit, joints and mounts that fabricate on any laser cutter. I believe that I make laser cut models better by adding additional incisions like the ones over here and the one over here. In particular, I believe that I make the models more portable this way. But before I'm going to explain you in more detail what I mean by that, let's have a look at a definition of portability that we are all very familiar with. So if you look at this piece of code, it's very obvious that this is not particularly portable because it makes calls to machine-specific registers and machine-specific ports. So if you would run this piece of code on any other piece of hardware, there's a good chance it will not work, or probably won't work at all. So here's the same code written in Python, and you see that it doesn't make any calls to the machine-specific properties of the machine. In particular, of course, because it's also reusing an underlying C script here. That C script itself calls a method called playOS, which underlyingly makes reference to the different operating systems that the system could be supporting. And in a way, therefore, this piece of code can run on any different operating system and on a range of various machines. So this script is considered very portable. So in the context of computer science, portability is a measure of how easily an application can be transferred from one computer environment to another. But to tie it back to laser cutting, where we started out with, I was wondering what the same definition would mean in that context. So within the context of laser cutting, this would be a measure of how easily a laser cutting model can be transferred from one laser cutting environment to another. So what do I mean by a laser cutting environment? In this case, that is all the hardware that is involved in the process of laser cutting. So it's the laser cutter itself, it's the material, and it's to a lesser degree the material thickness that is involved in this process. Typically, if you make a change to any of these parameters of the laser cutting environment, there's a good chance that files do not work anymore. And so my goal in this research is to make models for laser cutting portable, make it work in any environment. One way of achieving this would be to create a parametric model and to generate the joints as you export them. This is great and this works pretty reliably, but it doesn't quite tie into the infrastructure that people are currently using for fabrication. You're using these 2D SVG files for laser cutting, and you don't have these type of capabilities when you're dealing with SVG files. So that's specifically what we are focused on here. So if we look at laser cut files, 19% of all models, they consist of single parts. So they are inherently portable. There's nothing that can go wrong here. However, the other 81% of models they are either 3D objects, they embed additional components, or they are larger than the laser cutter itself and therefore contain joints and mounts to make the model work in general. So here's a range of models that we actually made portable using our approach. And for the sake of this talk, I'm going to focus on one specific model and explain it in more detail. So this game controller here, if you zoom in a little bit further into that, has different types of joints and different types of mounts that make this model work. If you would change the laser cutting environment without considering what it does to these mounts and joints, there's a good chance the model does not assemble or does not fabricate well. So you get like situations like this, and I guess everybody who's been laser cutting a lot and especially downloading files from Thingiverse have encountered this situation. So if you zoom into one specific element of this model, this button here, let's see how this works out for that particular case. So in the original model, obviously it worked fine, right? The person who has been laser cutting this thing has tuned the parameters up to the degree that this button mounts really well in place. However, if you use a different laser cutter with bigger curve, there's a chance that the button will fall out or will not mount tightly in place. And at the same time, if you use the machine with smaller curve, it could crack the material, it could break the surrounding material. And the same thing happens if you change the material or if your laser cutter is in a different state of wear. So if your lens, for example, got dirty, again, the curve is influenced by this, and there's a good chance that models don't work as well as they used to work before. So if we look a little bit more in detail what is going on here, this is the cut of that button. It's a nice circle. And it's supposed to be slightly smaller than the original button size, and that's how it is press fit in place. So you compress the material around to kind of, with a very tight connection, fit that button in that hole. Unfortunately, there is a concept called curve, which is the amount of material that the laser removes when it's cutting. And that's the gray circle you see here. This is different for different laser cutters and for different configurations. So that amount of curve there causes that button to not fit tightly in place anymore. The typical way to handle this is to erode the file. So like figure out in the model where curve plays a role and then make all the adjustments to make sure that the curve, again, would now be fitting to exactly the same red line again. So in a way, you could port that model. You could adjust the SVG so it works for the specific laser cutter that you're using. But this is a very time-consuming and very tedious process, and it requires knowledge of not only the machine, but also a very much detailed knowledge of the model that you're trying to modify here. So we were wondering if we could, rather than having very specific size to support, if we could support a range of sizes here. And the answer, obviously, is yes, we can. We can achieve that by adding this additional cutout into the model. This thing is called a cantilever spring, which is a rigid structural element, such as a beam or plate, which is anchored at one point to support from which plate it protrudes. So now instead of, so we are not the only ones who used cantilever springs in 3D printing and laser cutting. So other people have done this as well. We are the first ones to use it in the context of making models portable, modifying the joints to make them portable. So rather than compressing the material, as I said before, we are now allowing the material to bend, and it's a lot more flexible to that. At the same time, we use the same concept to not only make those mounts portable, but also to make different types of joints. So here you see an example of a T-joint, a cross joint, and a finger joint that are all made portable with the same concept of cantilever springs, resulting in this game controller, which is now highly portable. So let's see how our software system supports us in making these type of portable models. In order to understand, we need to have a quick look at the architecture of the system. And in particular, that we, as I said before, we're trying to integrate the system as close as possible to the environment that people and the infrastructure that people are using for fabrication right now. So we want to use SVG as input and SVG as output as well. At the same time, we made a system that is running on a server and therefore very easily extendable and can be easily called by other software tools and systems. So it can be used as an extension of other systems. So let's see how it works in practice. We have a browser tool, and we load an SVG model in here. That's the model of the game controller we saw before. And it just displays the model itself in the UI. So the first thing we need to do is we need to specify the material thickness for SpringFit to understand where the joints are. So we use the material tool, and we click on one segment that has exactly the length of material thickness. And you see that immediately SpringFit responded by placing all the springs in the model where it thinks a spring should go. The way it does that is it looks for the segments that are labeled as material thickness, and it finds all the same ones in the model. And it looks at the adjacent segments to find out what the angles are with respect to that segment and how long they are. So that information is used in order to classify this particular thing here as a cross joint, and this one here as a finger joint. So if you have two parallel material thicknesses and a 90-degree angle in between, you can assume that this is a finger joint. We then generate the spring geometry, which is like this simplified cantilever spring you see here. And interestingly, this spring could perform the same way. So there is some adjusting we can do with the parameters of those particular springs. We can adjust the height, the length, and the amount of deflection that each of these springs support. And the way we do that, we optimize for the smallest possible spring, so the least aesthetic and structural impact in the model. And we don't want, of course, to break the material. So there's some sort of lower limit that we have to support in order to make sure that the springs work for all of the models that we're trying to support. We find this out by using a nonlinear optimization algorithm, which is called Kubaila, and which we run in the background of a software system. So that's how SpringFit figured out where all the joints are in this model. Last thing we need to do is to add the mounts there for the buttons. We can place them manually. We don't guess them ahead because there are typically less of those in the model. And once they are all placed, this model is essentially ready to be fabricated directly because it is an SVG and it is displayed directly in the browser. So you can send this out to your laser cutter and fabricate the result, which looks something like this. So this model now fabricated not only in plywood, but also in a different material. So we are now supported for all kinds of laser cutters and variations in material. So we evaluated the system both on a technical level and on a practical level. So on a technical level, we wanted to find out whether the springs that we generated actually perform how we hope they should perform, like whether they are performing to the spec that we set for them. So we slowly pushed a force sensor into the spring, And you will see, is it running? Yeah. That it slowly pushes it out up till the moment that the amount of deflection is reached that we had intended it to be, with the force that we required it to be. So we ran this for 10 samples for acrylic and for plywood and for different force profiles that we were looking for. And unfortunately, our calculations were correct, so this spring is not going to break. So the result of this analysis is that in this case, the force requirement was 5 newtons, and the amount of deflection that we wanted to support was 1 millimeter. And you see that both the acrylic and plywood easily outperform that spec, so like they are good enough to fulfill this requirement. And we did the same thing with larger amount of forces, and again, like we managed to make sure that the springs that we generate all perform according to the spec. So the last thing we did is we also wanted to find out how well this conversion works, how many models can we actually support this way. So we took 14 multi-part models, laser cut models from Thingiverse, of which 8 completely converted automatically. So there's these 8 models. There was no need for any human intervention to make these models work off the shelf with the SpringFit system that you just saw. In 2 out of these models, there was like a situation where we could not resolve the problem. So here is a TIE fighter, which has a tiny little part in the front, which is press fit in place. So if we wanted to do that, the spring would be bigger than the part that we're trying to hold. In this case, we can unfortunately not support the geometry. And the same is going on with this dragon here. So there were 2 models here that had like such small features that we could just not create a spring in there. So these are beyond the scope of what we can handle. At the same time, there was one model which consisted of circular or like kind of radial spring finger joints. And unfortunately, our classification algorithm did not detect these as finger joints, which can obviously be implemented, but for the time being, this was also not supported by our algorithm. So in conclusion, we managed to make a large amount of models portable across different materials and any laser cutter. And so if you look at the laser cutting environment that we started out with, we now have models that work on any laser cutter, work for a range of materials, and to a smaller degree work on different material thicknesses, but more work is going to go into also supporting that for portable fabrication. And if you zoom out a little bit further, with the increase of like more available and more cheaply available fabrication machines, and also a larger diversity of laser cutting machines that are being created at the moment, the question of portability and maintainability of files becomes ever more prevalent. It's like we are sharing more files, we have more different machines that we want to support, but at the same time, the files that we are sharing right now are simply not working on other fabrication machines. So we believe that in the near future, the question of portability and maintainability will become an even bigger question. Therefore, we should start to look into making files that can be supported for different laser cutters. So on that note, I would like to thank you for your attention and welcome the questions.
Does anyone have any questions for Thijs? Oh, right there, Stephanie.
Stephanie Müller, MIT-CC. Hi, Thijs. So if it comes down to the question of I have an existing file and I want to fabricate that on a machine that's other than the one where the file was created, do you have any other thoughts on how this could be done? So I could imagine I remember we had like a calibration strip, you could cut and maybe take a photo. What's the benefit of, why did you go for this one versus maybe some other approach? I'm sure you brainstormed more options.
Yeah, so there are certainly different ways of doing this, right? You could indeed try to find out exactly what the specifics of your laser cutter are and trying to optimize a file for that specific spec. I think there is a certain beauty in having a general file, like a generic file, so a file that works like off the shelf for any laser cutter that you'd be using. So you wouldn't even need to kind of go and measure and kind of figure out how your laser cutter performs. So this one you can just reliably trust, and you also, when you're sharing it online, you don't put a constraint on the other person that they have to again measure their laser cutter to then make it work. So this is like the least overhead kind of form of maintaining the file, but obviously more things can be done, yeah.
Anybody else with a question? Oh.
Hi, Emily Whiting, Boston University. Really nice work. So just one question on how does this scale. So if I was to like scale down or scale up the model, do the stiffness values and the other parameters work in that way, or do they have to be recalibrated? Or what
Yeah, so I would, if you change the scale of the model, I would recommend to pipe it again through the tool, and then it will work again. If you would just linearly start to scale the springs, obviously their spring performance starts to vary as well. So I would not recommend to first put springs, then change the scale, and then try to fabricate it, because that would result in springs that are either way too tight or that are too weak, and that might actually break. So we cannot guarantee that these constraints are maintained.
Thanks.
Thank you.
Any last questions? Okay, I actually have a question. Fifth presentation, first time I have to ask, which is fabulous. Thank you, guys. So what if you wanted to laser cut a material that does have a little bit of flexibility in it, but not enough to actually push your components? So like a foam. How could you or would you be able to change the spring mechanism?
Yeah, so when we were generating the standard springs that you saw in the system so far, we tried to support, make them work for the range of materials that are typically used for fabrication, for laser cutting. If you would come with very specific materials, like, for example, metals or foams, these are further out in the stiffness spectrum. So they have like Young's modulus that are very extreme, and there are limitations. So at some point, we cannot make that work anymore. So I would say, like, when you go towards metals, probably press fit is also not the best way of joining parts together. You're better off welding, for example. And the same with foams. Maybe a press fit connection is also not the most sturdy way of connecting two foams to each other. So there's like some sort of limit of where press fit in general plays a role. And within that scope of materials, we do very well with our springs. Things that are far outside that scope are not supported by our system right now.
Perfect. Thank you, Thijs. If we could give him a round of applause again.